Subscribe to the channel and like the video. Somewhere, far beyond the reach of even our most powerful rockets, in a realm of space so distant that its light takes 1 billion years to arrive at our eyes, there exists a colossus, a cosmic leviathan that makes our own Milky Way look like a speck of dust in a boundless ocean. Meet IC 1101, a galaxy so vast, so overwhelmingly large, that the human mind struggles to wrap itself around its dimensions. Imagine stretching a ruler across the sky, not in kilometers or miles, but in millions of light-years, each light-year being nearly 9.5 trillion kilometers, and you still wouldn't reach its edge without counting all the way past 6 million of them. Let that sink in. Our home galaxy, the Milky Way, is a proud and beautiful spiral about 100,000 light-years wide. We're used to thinking of it as enormous. After all, it holds hundreds of billions of stars, nebulae, and planets. But when placed next to IC 1101, the Milky Way is like a small town next to a sprawling continent. If the Milky Way were the size of a silver coin, IC 1101 would be bigger than a city plaza. This is not just a big galaxy, it's a record-breaking skyscraper in the cosmic skyline, one of the largest known galaxies in the observable universe. And the sheer enormity of it isn't just in physical size. IC 1101 is an ancient elder of the cosmos, a survivor and conqueror, having grown through countless galactic mergers over billions of years. It's a place where the night sky, if we could stand within it, might be ablaze with the golden glow of countless suns, where distances between stars could be far tighter in some regions, and the pull of gravity would feel like an ever-present hand guiding the dance of matter on a colossal scale. When we look at IC 1101, we aren't just looking at a galaxy, we're looking at a piece of the universe's biography, a chapter written over 10 billion years, chronicling how smaller galaxies fell together, collided, and were absorbed into one sprawling empire of stars. It's a silent monarch at the heart of its kingdom, the Abell 2029 galaxy cluster, ruling with the invisible but undeniable force of gravity. But there's another detail that deepens the awe. When we observe IC 1101, we are peering back in time by 1 billion years. That means the light we see tonight began its journey long before human civilization, before the Earth's continents took their current shape, before the ancestors of mammals roamed the land. That light started traveling while dinosaurs were still walking our world, and it's only just reaching us now. IC 1101 is not just an astronomical curiosity. It's a humbling reminder that the scale of the cosmos dwarfs every mountain, every city, every dream we've ever had. It is a cosmic titan that stretches our imagination to its breaking point, and still leaves us with the feeling that the universe may have even larger giants waiting to be discovered. The name IC 1101 may sound like a cold, technical label, but behind those 3 characters and 4 digits lies a history that reaches back more than a century. The IC stands for Index Catalog, a monumental supplement to the earlier New General Catalog, NGC, which was itself one of the most ambitious attempts to organize and identify the vast variety of celestial objects seen through telescopes. In the late 19th and early 20th centuries, astronomers were piecing together a vast cosmic address book, one galaxy, star cluster, and nebula at a time. The Index Catalog was published in 2 parts, the first in 1895 and the second in 1908, and was compiled by John Louis Emil Dreyer, a Danish-Irish astronomer who dedicated much of his life to cataloguing the heavens. Within this catalogue, IC 1101 earned its spot, an unassuming entry that gave no hint at the time that it represented one of the largest galactic structures in the observable universe. Its discovery traces back even earlier, though. In 1890, using the telescopes of the era, which by today's standards would seem modest but at the time were at the cutting edge of astronomical technology, astronomers peered into the night sky and identified this faint smudge of light in the constellation Virgo. Historical records connect its classification to follow-up work stemming from the legacy of William Herschel, one of the most important astronomers in history, who had compiled vast lists of nebulae and clusters during his lifetime. Herschel himself passed away in 1822, decades before IC 1101's entry into the catalogue, but his systematic approach to surveying the heavens laid the foundation for the later expansion of these catalogues. By the time Dreyer and others were adding objects like IC 1101 to the Index Catalog, Herschel's observational techniques and meticulous records had become standard practice in professional astronomy. In the late 19th century, the very idea of a galaxy as we understand it today was still far from mainstream. Astronomers then referred to these faint patches of light as nebulae, unsure whether they were distant, self-contained star systems like our Milky Way or simply clouds of gas within our own galaxy. The true nature of galaxies wouldn't be settled until the 1920s, when Edwin Hubble proved that certain spiral nebulae were in fact separate island universes far beyond the Milky Way. That means when IC 1101 was first recorded in 1890, it was just another misty blur in the eyepiece, with no inkling that it was an ancient titan hundreds of times larger than our own galaxy. The telescopes of that era could not begin to resolve the fine details we now associate with IC 1101. What was seen then was merely the concentrated central light from billions upon billions of stars, blurred into a luminous haze by its immense distance. Its true size was not measurable at the time, because distance measurements were rudimentary. The speed of light travel time to such an object, around 1 billion years, was incomprehensible to late 19th century observers. To them, IC 1101 was simply one of many faint and mysterious objects scattered through the night sky, catalogued dutifully so that future astronomers could study them in greater detail. That act of cataloguing, of recording its position, brightness, and appearance, was in itself an extraordinary achievement for the time. The index catalogue was like a lantern illuminating the path for future discoveries. Without those systematic records, modern astronomers might never have connected the dots that revealed IC 1101's extraordinary nature. It's fascinating to think that when the entry for IC 1101 was first inscribed into the catalogue, it was just an anonymous entry among thousands, unremarkable except for the fact that someone had taken the time to mark it down. The breathtaking revelation of its enormity would only come much later, as technology advanced and the field of astronomy evolved into the era of large observatories and space-based telescopes. When you consider that this discovery predates the invention of the airplane, the theory of relativity, and even the concept of galaxies as separate universes, you start to appreciate the patience of science. Knowledge doesn't always arrive in dramatic bursts. Sometimes it's a slow build, a layering of observations over decades, even centuries. IC 1101's story began as a faint in the eyepiece, labeled and filed away in a catalogue. It would take generations of astronomers, improved telescopes, and a much deeper understanding of cosmic distances to realize that this wasn't just another galaxy. It was one of the ultimate giants of creation, a record setter on the grandest scale imaginable. What began as a small mark in an astronomer's ledger in 1890 would one day emerge as a colossus that could engulf dozens of Milky Way-sized galaxies without effort, a staggering reality that the discoverers could never have imagined. If you were to step outside on a clear night, far from city lights, and gaze up into the darkness toward the constellation of Virgo, your eyes would be falling on the general region where IC 1101 resides. Of course, you wouldn't see it, not without a powerful telescope, because at a distance of about 1 billion light-years, even something 6 million light-years wide is reduced to a faint smudge of light. The human eye, marvelous though it is, was never built to take in the soft whisper of photons that have been traveling for 1 billion years through intergalactic space just to reach us. Yet that's exactly what happens when astronomers aim their instruments toward Virgo and tune into the signal from this distant titan. Virgo itself is a constellation steeped in astronomical significance. It's the second largest constellation in the sky and a rich hunting ground for galaxies because it sits in the direction of the Virgo cluster, a vast collection of galaxies that's relatively close to our own local group. But IC 1101 is not part of that nearby cluster. Instead, it lives far beyond, in a deeper layer of the cosmic tapestry. Its light comes to us from a time when Earth's continents were still shifting toward their current positions, and life was continuing its slow evolutionary climb toward what would one day become the age of mammals. The distance is staggering. 1 billion light-years means that the light we see left IC 1101 when the Earth was in the middle of a completely different chapter of its history, long before any human eyes existed to receive it. Locating IC 1101 in the sky is a bit like trying to spot a single grain of sand in an endless desert. The constellation Virgo serves as a convenient signpost, but you need far more than naked eye navigation to find it. Astronomers pinpoint it using precise coordinates, right ascension and declination, which are like the latitude and longitude of the sky. Its position is catalogued with exactness because without that, trying to revisit its location with a telescope would be like trying to find the same dust mote in a sunbeam day after day. And in that precise spot, seemingly empty to casual observation, lies a city of 100 trillion stars bound together by gravity, shining across 1 billion years of space-time. Being so far away also means that IC 1101's light has traveled through an unimaginable stretch of cosmic scenery before arriving here, past intergalactic gas clouds, through regions where other galaxies roam, and across voids so empty that a beam of light can travel millions of years without encountering a single atom. That uninterrupted journey gives us a kind of time machine. We see IC 1101 not as it is today, but as it was a billion years ago. In that sense, the galaxy we know from our telescopes is already a historical artifact, frozen in the light it emitted eons before humans were capable of understanding what a galaxy even was. What's especially poetic about its location is that the constellation Virgo has long been associated with myths of harvest and fertility, symbols of abundance and creation. IC 1101, in its own way, embodies a cosmic abundance beyond anything those ancient stories could have imagined. A gravitational empire in space, rich not in grain or fruit, but in suns, planets, and the relic glow of ancient stellar generations. When you realize that it sits a billion light-years away, it's humbling to think about the sheer vastness of space between us and it. That gap is not just distance, it's time, history, and the difference between two completely separate chapters of the universe's life story. IC 1101 does not drift alone in the cosmic dark. It is the heart and ruler of an entire galactic metropolis known as Abell 2029. Imagine, for a moment, a city so vast that it isn't measured in blocks or kilometers but in millions of light-years, with each building being a galaxy, each containing billions or trillions of stars. That is what Abell 2029 is, a gravitationally bound gathering of thousands of galaxies, all swirling together in a titanic dance orchestrated by the invisible threads of gravity and dark matter. And right at its center, like the Grand Palace at the heart of an ancient empire, sits IC 1101, dominating its surroundings in both mass and scale. Abell 2029 is what astronomers call a galaxy cluster, but to understand just how massive it is, you need to set aside any idea of proximity we experience on Earth. The galaxies within the cluster may be part of the same family in the gravitational sense, but they are still separated by millions of light-years of space. The binding force that keeps them together is the combined mass of everything in the cluster, not just stars and planets, but also vast oceans of hot gas and enormous amounts of dark matter, the mysterious substance that outweighs all the visible matter in the universe and yet cannot be seen directly. Abell 2029's mass is so great that it warps the very fabric of space-time, bending the paths of light traveling near it in a phenomenon called gravitational lensing. Through this effect, distant background galaxies are sometimes magnified or distorted when we observe them through the cluster's location. For IC 1101, this environment is both a home and a source of nourishment. Sitting at the cluster's gravitational core, it acts like a sinkhole in space, slowly drawing in other galaxies that venture too close. Over billions of years, this process has allowed IC 1101 to grow far beyond the size of a typical elliptical galaxy, swallowing smaller galaxies whole and incorporating their stars into its golden glow. The center of Abell 2029 is a place of intense gravitational dominance, and IC 1101 is the undisputed monarch. The space between galaxies in Abell 2029 is not empty in the way we often imagine space to be. It is filled with scorching plasma heated to tens of millions of degrees, radiating strongly in X-rays. This hot intracluster medium, detectable only through specialized instruments, is evidence of the turbulent interactions and energy exchanges taking place within the cluster. The galaxies within Abell 2029 are not static. They move in orbits determined by the cluster's mass, sometimes passing close enough to one another to cause gravitational disturbances that can strip stars or gas away from their outer edges. These encounters, while spanning unimaginable distances, are a key part of the ongoing story of IC 1101's growth. What makes Abell 2029 especially impressive is its sheer size and density. While our own local group, which contains the Milky Way, Andromeda, and a few dozen smaller galaxies, is only a tiny gathering on the galactic scale, Abell 2029 is a supercity of the cosmos. Thousands of galaxies coexist there, their combined light creating a faint, diffuse glow when viewed through the most powerful telescopes. And in the center of it all, IC 1101 sits like the massive beating heart of the system, its gravitational reach stretching far into the cluster's core. Being part of such a rich cluster is likely the reason IC 1101 reached its monstrous size in the first place. In the cosmic wilderness, galaxies rarely achieve such extremes, because there simply aren't enough nearby companions to feed their growth. But in Abell 2029, mergers and interactions are part of the natural order. It's a place where galaxies live fast in cosmic terms, colliding, blending, and fading into one another, all while the central giant grows ever larger. In this environment, IC 1101 isn't just another galaxy. It's the gravitational anchor that shapes the destiny of thousands of its neighbors. When we talk about the size of IC 1101, the numbers almost stop feeling real. Over 6 million light-years across, that's not just large, it's the kind of large that bends your ability to picture it. A light-year, the distance light travels in a single year, is about 9.46 trillion kilometers. Multiply that by 6 million, and the figure you get is so huge it might as well be written in another language, because the human mind has no frame of reference for distances of that magnitude. And yet, IC 1101 occupies exactly that kind of territory in the cosmos. To appreciate just how big this is, you have to compare it to something we know, our own Milky Way. The Milky Way, with its graceful spiral arms and bustling neighborhoods of stars, is about 100,000 light-years across. To scale that against IC 1101 is like putting a grain of sand next to a dinner plate, and that's being generous to the grain of sand. In fact, you could line up about 60 Milky Ways side by side inside IC 1101 and still have room to spare. That means IC 1101's edge-to-edge reach is not just a little bigger, it's orders of magnitude larger than the galaxy we call home. And the difference isn't just in width, it's in volume. If you imagine the Milky Way as a three-dimensional object, then increase its dimensions 60-fold in all directions, you're looking at something with millions of times the volume. The amount of space IC 1101 occupies is so great that you could drop the entire local group, which contains the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller companions, into it and still be lost somewhere deep inside, with vast gulfs of space separating you from its outer rim. This scale has profound consequences for everything within it. In a galaxy of such immensity, light from the farthest outskirts might take tens of millions of years just to reach the core. The sheer number of stars, planets, and potential star systems spread across that span is staggering. If civilizations existed in different corners of IC 1101, the act of communicating would be an epic exercise in patience. Messages sent by light-speed signals could outlast entire species before arriving at their destination. In physical terms, it's almost misleading to think of IC 1101 as a single galaxy in the same sense we think of the Milky Way. It is more like a galactic continent, the product of countless mergers, stretching across a chunk of space so large it begins to blur the lines between individual galactic identity and a cluster in miniature. Standing within such a system, if standing is a concept that makes sense in a place so vast, you would be surrounded on all sides by an ocean of golden light, the glow of billions of stars from countless former galaxies now assimilated into one. The enormity of IC 1101 also forces astronomers to think about the limits of what is possible for galaxy formation. Most galaxies never come close to such dimensions. Spirals like the Milky Way tend to top out around a few 100,000 light-years at their most extended. Even large elliptical galaxies, which are already swollen from past mergers, rarely exceed a couple of million light-years in diameter. But IC 1101 has pushed past those limits, ballooning to more than 3 times the size of the next tier of giants. That kind of growth requires an environment rich in fuel, other galaxies to consume, and billions of years of uninterrupted expansion. When you realize that the galaxy's outermost stars are separated by such distances that even the concept of inside the galaxy becomes almost abstract, you start to understand why IC 1101 stands in a league of its own. It is not just a large galaxy. It is a structure so vast that it challenges our definitions, a cosmic superstructure built on a scale that dwarfs everything we know. The Milky Way is our home, and we rightly marvel at its beauty and scale, but next to IC 1101, it is a quiet suburban street compared to the glowing sprawl of an endless city. If the size of IC 1101 is difficult to comprehend, the number of stars it contains is even more staggering. Current estimates place its stellar population somewhere around 100 trillion stars, and possibly more. That number, written out in full, is 100 trillion, each one a sun in its own right, some larger and hotter than our own, some cooler and dimmer, and all bound together by the galaxy's overwhelming gravity. When astronomers look at such a colossal system, the figures they deal with stop feeling like numbers and start feeling like symbols of something beyond human intuition. For a point of comparison, the Milky Way is thought to contain somewhere between 200 billion and 400 billion stars. That's already enough to overwhelm the imagination. Stand outside on a clear night in a dark sky location, and the band of the Milky Way stretching across the sky represents just the tiniest fraction of our galaxy's full stellar population. And yet, IC 1101 contains hundreds of times more stars than that. It's not just another step up the ladder. It's a leap into a whole new category of galactic abundance. In a galaxy with so many stars, the diversity of stellar types is almost certain to be extraordinary. Red dwarfs, small, cool, and long-lived, likely make up the majority, just as they do in the Milky Way. These would be accompanied by countless yellow main sequence stars similar to our Sun, scattered among vast populations of aging red giants, which bathe the galaxy in a soft golden glow. There would also be remnants of stellar death, white dwarfs, neutron stars, and perhaps billions of black holes of stellar origin, each one the corpse of a star that once burned brightly in IC 1101's ancient past. This incredible number of stars means IC 1101's total light output is enormous, though distance robs it of brightness to our eyes. Seen up close, the collective radiance of 100 trillion suns would flood the skies, making the night nearly as bright as day in some regions. Even in the outer reaches, the glow of so many stars packed into the galaxy's volume would be unmistakable, a golden haze marking the presence of uncountable suns. And yet, the sheer number of stars is only part of the picture. Consider the worlds that might orbit them. If even a small fraction of IC 1101 stars host planetary systems, the number of planets in the galaxy could be beyond anything we can truly calculate, potentially hundreds of trillions or more. Some of these worlds would be barren, others could be covered in oceans or ice, and perhaps, on a rare few, life might have taken root. But because of the galaxy's size, civilizations on opposite ends of IC 1101 would be so far apart that they might as well be in different universes, their signals unable to cross the galaxy in less than tens of millions of years. The sheer scale of its stellar population also adds to IC 1101's gravitational might. The combined mass of so many stars, along with the dark matter halo surrounding them, makes it one of the most massive galaxies ever observed. This mass not only binds the galaxy together but influences the orbits of other galaxies in Abell 2029, effectively making IC 1101 the gravitational anchor of its entire cluster. When you step back and try to imagine it, 100 trillion stars scattered across 6 million light-years, the reality is almost impossible to hold in your mind. Our galaxy feels immense when we consider its hundreds of billions of stars, but in the realm of IC 1101, even the Milky Way would be just another minor component swallowed by the giant's appetite for growth. The difference is so extreme that it makes our galaxy feel small in a way we rarely contemplate, a humble reminder of just how varied and grand the universe's creations can be. IC 1101 is not the kind of galaxy you describe as flashy or full of dramatic structure. It doesn't have the graceful spiral arms of the Milky Way or the whirlpool-like beauty of Andromeda. Instead, it is a supergiant elliptical galaxy, a colossal, oval-shaped system with a smooth, almost featureless appearance when viewed through a telescope. Where spiral galaxies are dynamic and intricate, ellipticals like IC 1101 are understated, their elegance lying in sheer scale and the uniformity of their glow. The shape of an elliptical galaxy is the result of countless mergers and collisions over billions of years. Each time two galaxies meet and merge, their orderly structures are disrupted. Spiral arms are shredded, star-forming regions are scattered, and the orbits of billions of stars are randomized. Over time, this chaotic gravitational mixing smooths out the shapes, producing the rounded, football-like profile we associate with elliptical galaxies. For IC 1101, this process has happened on a grand scale, erasing any signs of a structured past and replacing them with a soft, golden haze stretching across millions of light-years. That golden glow is one of the defining features of supergiant ellipticals. It comes from the light of billions upon billions of older stars, mostly yellow and red in color, that dominate the population. These stars are cooler than the hot, blue, short-lived stars found in younger galaxies, and they radiate a warm hue that bathes IC 1101 in a rich, aged light. The uniformity of its color tells astronomers that IC 1101 has very little ongoing star formation. The brilliant blue stars of youth are missing, having long since burned out or aged into redder, cooler forms. This golden sheen is like the fading embers of a once roaring fire, still bright, but clearly past the stage of new fuel being added. As a supergiant elliptical, IC 1101 belongs to an exclusive class of galaxies. While ordinary ellipticals can range from small, dim systems to fairly large ones a few 100,000 light-years across, supergiants like IC 1101 go far beyond that. They occupy the extreme end of the galactic size spectrum, often sitting at the centers of massive galaxy clusters. Their sheer gravitational dominance allows them to act as cosmic scavengers, pulling in smaller galaxies and absorbing them over eons. This relentless growth is why their shapes remain smooth. They are built from the remnants of countless others, blended into one enormous whole. From a distance, IC 1101 might seem deceptively simple in appearance, just an immense, softly glowing oval against the blackness of space. But that simplicity hides a violent and dynamic history. The shredded remains of spiral arms, the collisions of galactic cores, the stripping of interstellar gas during high-speed encounters. Every star in its population carries with it the story of a galaxy that once was, now assimilated into the vast elliptical structure. Its smoothness also makes it more challenging to appreciate visually compared to more photogenic spirals. In astrophotography, spiral galaxies draw the eye with their delicate arms and dust lanes, while ellipticals look almost plain. But in the case of IC 1101, what you're seeing is the final form of galactic evolution, the cosmic equivalent of a mountain worn smooth by eons of wind and weather. It is the end product of billions of years of growth and change, a serene giant whose calm exterior hides the turmoil of its formation. Standing in the middle of IC 1101, if such a thing were possible, you would be surrounded by that golden light in every direction. The stars would be evenly scattered, without the dramatic concentrations of gas clouds and spiral arms that we know in the Milky Way. There would be no obvious central bulge or arms to orient yourself by, only an endless sea of aging stars, stretching as far as light could travel in millions of years. In its understated way, IC 1101 is a masterpiece of cosmic architecture. Smooth, vast, and built on a foundation of countless stellar generations. The first thing you'd notice about IC 1101, if you could see it up close with your own eyes, wouldn't be the intricate shapes that spirals boast, but rather its color, a soft, yellowish gold that permeates the entire galaxy. This color is not an accident of perspective or a trick of light. It's a direct fingerprint of the stars it contains. Astronomers have long used color as a diagnostic tool, because a galaxy's hue tells a story about the ages of its stars and the pace of its ongoing stellar birth. In the case of IC 1101, that warm golden tint is the calling card of an ancient population. Young galaxies, or galaxies still rich in star formation, tend to sparkle with intense blues and whites. Those shades come from massive, hot, short-lived stars, the kind that burn through their fuel in only a few million years before exploding as supernovae. These stars flood their galaxies with blue light, masking the presence of older, cooler stars beneath them. But those youthful bursts don't last long on cosmic timescales. Once the available cold gas runs out, star formation slows, the blue giants disappear, and the older, redder stars take over the visual stage. That is exactly what has happened in IC 1101. Its yellowish glow comes from billions upon billions of stars that are cooler and older than the Sun. Most of these stars are in the later stages of their lives, having burned steadily for billions of years. The fact that they dominate the galaxy's light tells us that IC 1101 hasn't had significant star-forming activity in a very long time, possibly for billions of years. Whatever cold gas it once possessed has been either consumed in earlier bursts of star formation, stripped away during galactic mergers, or heated so much by gravitational interactions and the hot intracluster medium that it can no longer cool and condense into new stars. This lack of fresh stellar birth changes the galaxy's personality. Spirals, with their active star-forming regions, are dynamic places, filled with bright nebulae and clusters of newborn stars. IC 1101, by contrast, is serene in its maturity. Its light is steady and uniform, not punctuated by the blue-white sparkles of young stars. In this sense, it's a galaxy in retirement, still radiant, but with the energy of youth long behind it. That doesn't make it lifeless. It's still home to a vast stellar population, but its stellar society is one of elders rather than infants. From a cosmological perspective, the color of IC 1101 also hints at its long history of mergers. When smaller galaxies merge into a larger elliptical like this one, the process tends to disrupt star formation. The collisions stir up and heat the interstellar gas, preventing it from cooling into the dense clouds needed for new stars to form. Over time, These processes leave behind a galaxy rich in old stars but poor in the raw materials of creation. The golden color is essentially the fossil light of stars born in earlier, more active epochs, now shining steadily as the galaxy coasts into the later stages of its life cycle. Seen from within, that yellowish tint would color the entire sky. Imagine looking up from a planet orbiting a star in IC 1101 and seeing not the dark velvet backdrop we're used to, but a canvas filled with warm, amber light from countless neighboring suns. There would be no vibrant blue highlights from hot young clusters, no sprawling star-forming regions painting the view, only the dignified, ancient glow of a galaxy that has lived through eons and shows it in its light. In the end, the color of IC 1101 isn't just an aesthetic detail, it's a testament to time. Every golden ray that reaches us from across a billion light-years is the combined voice of an ancient stellar population, whispering the story of a galaxy that grew vast and mighty but now shines with the quiet confidence of age. When astronomers speak of IC 1101's mass, the numbers they use push language to its breaking point. This galaxy is thought to contain on the order of 100 trillion times the mass of our Sun, and that's just the stellar and visible matter. Factor in the invisible dark matter halo surrounding it, and the total mass could be significantly higher. It's a figure so colossal that it's easy to say the number but far harder to truly understand what it represents. This is not just a large galaxy. It is one of the most massive single objects humanity has ever identified in the observable universe. Mass, in the context of a galaxy, is not just about the number of stars. IC 1101's immense gravitational field is the sum of all its components. Stars, planets, stellar remnants, supermassive black holes, hot gas, and the vast, unseen ocean of dark matter that envelopes the galaxy and its cluster. This gravitational force is not a static thing. It actively shapes the environment around it. Other galaxies that stray too close to IC 1101's territory can find themselves drawn inward, their stars and gas stripped away and absorbed. This process is slow on a human timescale, but relentless on the cosmic one, a steady, inevitable pull that has been at work for billions of years. To put the gravity of IC 1101 in perspective, consider the escape velocity of our Milky Way. Near our galaxy's sun-like distance from its center, you'd need to be traveling at hundreds of kilometers per second to break free of its gravitational hold. In IC 1101, those figures rise dramatically. The stars in its outer regions are still bound by its pull despite orbiting millions of light-years from the core. The gravitational reach of this galaxy is so immense that it anchors not only its own stellar population but also influences the orbits of galaxies throughout the Abell 2029 cluster. In this sense, IC 1101 isn't just a galaxy, it's a gravitational anchor for an entire galactic metropolis. The power of that gravity also plays a role in the galaxy's internal structure. Stars in IC 1101 don't orbit in neat, orderly paths like in a spiral galaxy. Their movements are far more random, the result of ancient collisions and mergers that scattered them into all directions. Yet despite the apparent chaos of these motions, every star remains bound by the central gravitational well, each one contributing its own infinitesimal tug to the galaxy's collective mass. That mass, concentrated toward the center but extending outward in the diffuse halo, defines the galaxy's overall shape and keeps its sprawling form intact. What's even more astonishing is that the visible matter, all the stars, planets, and glowing gas we can detect, is likely just a fraction of IC 1101's total mass. The majority is dark matter, invisible to our instruments but revealed through its gravitational effects. Without this dark matter, the outer stars and companion galaxies wouldn't be able to move the way they do. They'd simply drift away into intergalactic space. Instead, dark matter holds everything together, extending IC 1101's gravitational influence far beyond its visible boundaries, like an invisible scaffold propping up the entire structure. If you were somehow standing on a planet deep within IC 1101 and could sense the galaxy's mass in the way you can feel the pull of Earth's gravity, the scale would be incomprehensible. Every direction you turned, there would be trillions of stars pulling at you, their combined force bound together by a dark matter halo that stretches far beyond what your eyes could see. The galaxy's gravity is the invisible ruler of this realm, shaping its history, feeding its growth, and slowly gathering more material into its colossal frame. In short, IC 1101's mass isn't just a statistic. It is the reason for everything the galaxy is. Its size, its shape, its dominance in Abell 2029, and its ability to swallow other galaxies all come down to the same thing: the overwhelming gravity of a system with 100 trillion solar masses. On the grandest scales, gravity is the universe's sculptor, and IC 1101 is one of its most monumental works. IC 1101's enormity didn't happen overnight. It wasn't born 6 million light-years wide, packed with 100 trillion stars. Instead, it is the result of billions of years of slow but unstoppable growth, fueled by one of the most transformative processes in the cosmos: galaxy mergers. These are not delicate encounters, they are gravitational battles that unfold over hundreds of millions of years, reshaping the participants and leaving behind something new, bigger, and often completely different from what came before. In the earliest days of the universe, galaxies were much smaller and more irregular. The very first ones were little more than star clusters bound together by gravity, but they existed in a cosmos far denser than today. Matter was clumped more closely, and galaxies were closer neighbors, making interactions much more likely. IC 1101's ancestor was probably one of these smaller proto-galaxies, born when the universe was only a fraction of its current age. Over time, it began to grow by pulling in others nearby, its gravitational field acting like a net. Each time another galaxy fell toward it, the two would collide in a slow-motion dance that eventually ended in a merger. When galaxies merge, their stars rarely collide directly. The distances between individual stars are simply too vast. Instead, gravity rearranges their orbits, redistributing them into new patterns. Gas clouds, on the other hand, slam into one another, triggering bursts of star formation. In IC 1101's case, this cycle repeated countless times. It consumed spiral galaxies, irregular galaxies, and other ellipticals, stripping them of their stars and gas and folding their matter into its own bulk. With every merger, its mass increased, its gravitational pull strengthened, and its ability to capture even more galaxies grew. Over billions of years, this process snowballed. Being at the center of Abell 2029 gave IC 1101 a constant supply of potential mergers. Smaller galaxies wandering too close would spiral inward, dragged by the cluster's gravitational currents until they were engulfed. Some would be completely absorbed, their stars scattered into IC 1101's smooth elliptical halo. Others might be torn apart before they even reached the core, leaving long streams of stars, tidal tails, that eventually faded into the galaxy's glow. Each one became part of the ever-expanding population of old, yellow stars that define IC 1101 today. These mergers also erased any original structure the galaxy might have had. If its earliest form was a spiral or irregular galaxy, those shapes were long ago scrambled beyond recognition. The ordered rotation of a spiral disk cannot survive the violent gravitational turbulence of multiple mergers. Instead, the star's motions became random, creating the smooth, featureless shape we see today. The more IC 1101 grew, the more it slowed its own star formation, not because it lacked stars, but because it was running out of the cold gas needed to make new ones. Much of that gas had either been consumed in earlier bursts of creation or heated to the point where it could no longer collapse into new suns. In many ways, IC 1101 is the ultimate expression of this process. While mergers are common in the universe, even our Milky Way is on course to merge with Andromeda in about 4 billion years. Few galaxies have both the time and the environment to reach such extremes. IC 1101 has had more than 10 billion years in a galaxy-rich environment to grow, and its location at the center of a massive cluster has provided a steady flow of material to feed its expansion. What stands today is not the work of a single cosmic event, but the accumulation of countless interactions, each one adding a little more mass, a few more stars, and a slightly stronger gravitational field. It's a slow kind of inevitability. The bigger it became, the harder it was for anything nearby to resist its pull. And so, over cosmic ages, IC 1101 grew from a modest galaxy into the colossal ruler of Abell 2029, a monument to the power of mergers and the patience of time itself. IC 1101's position in Abell 2029 isn't just a matter of chance, it's the key to its dominance. This galaxy sits in the very heart of the cluster, occupying the deepest part of its gravitational well. You can think of a galaxy cluster's gravity as a vast, invisible bowl carved into the fabric of space-time, and IC 1101 lies at the very bottom of that bowl. Everything in the cluster, the thousands of galaxies, the oceans of hot gas, the mysterious dark matter, is drawn toward this central region. Being in that prime location has allowed IC 1101 to act as both ruler and scavenger, growing ever larger as it steadily gathers more material from its surroundings. The center of a galaxy cluster is a dangerous place for smaller galaxies. The gravitational pull here is relentless, and the speeds at which galaxies move through the cluster can be extreme, thousands of kilometers per second. As smaller galaxies pass near IC 1101, tidal forces begin to tear them apart. Stars are stripped away first, forming faint halos or streams that eventually blend into the giant's smooth outer regions. The cold gas they might have carried is heated and dispersed into the hot intracluster medium, further enriching the environment but making new star formation in IC 1101 unlikely. It's not only galaxies that IC 1101 feeds upon. The center of Abell 2029 is also home to enormous reservoirs of hot gas. While this gas is too warm to collapse into new stars under normal conditions, it still contributes to the galaxy's overall mass and may occasionally cool enough to trigger small bursts of star formation deep within the core. Most of the time, though, the energy from the cluster, and perhaps from a central supermassive black hole in IC 1101 itself, keeps the gas heated, preserving the galaxy's golden, elderly character while still adding to its gravitational influence. The gravitational reach of IC 1101 extends far beyond its visible edges. This isn't just a galaxy with a big halo. Its mass is so great that it influences the movement of galaxies millions of light-years away. Some astronomers even suspect that its dark matter halo is intertwined with the larger dark matter structure of the entire cluster, making IC 1101 not just a resident but an integral part of the cluster's skeleton. Its presence shapes the dynamics of Abell 2029, dictating how galaxies orbit, merge, and evolve over cosmic time. This central position also means that IC 1101 is constantly fed by the natural flow of the cluster. Galaxy clusters aren't static. They grow by drawing in material from their surroundings through vast filaments of the cosmic web. As fresh galaxies and gas flow into Abell 2029 from the surrounding universe, much of it eventually migrates toward the center. And waiting there, like a patient predator, is IC 1101, ready to add these new arrivals to its empire. Over billions of years, this process has allowed it to swell to its current size, and there is no reason to think it has stopped. If you could watch the history of Abell 2029 in fast forward, you'd see IC 1101 as a luminous heart that steadily grows brighter and more massive, absorbing neighbor after neighbor while the cluster's outer edges slowly funnel material inward. The rest of the galaxies in the cluster live in a delicate balance, some destined to remain in stable orbits, others fated to be drawn inexorably toward the central giant. In this way, IC 1101 is more than just a galaxy within Abell 2029. It is the gravitational anchor around which the cluster's cosmic drama plays out. At the heart of IC 1101, hidden behind its golden haze of ancient stars, there almost certainly lurks a monster, a supermassive black hole so vast that it would defy even the imaginations of most science fiction. In galaxies, the mass of the central black hole tends to correlate with the mass of the galaxy's bulge. For a galaxy like our Milky Way, which holds about 200 to 400 billion stars, the central black hole, Sagittarius A*, weighs in at about 4 million times the mass of the Sun. But IC 1101 is a galaxy on a completely different scale. With perhaps 100 trillion stars and a mass that makes our Milky Way look like a cosmic pebble, the black hole at its center could be among the most massive in the known universe. Some estimates suggest that such a galaxy might harbor a black hole in the range of 40 to 60 billion solar masses, and perhaps even more. That's a number almost too big to grasp. A black hole of that size would have an event horizon stretching well beyond the orbit of Pluto if it were dropped into our solar system. The sheer gravitational pull of such an object would be enough to dictate the motions of stars tens of thousands of light-years away. In IC 1101, that influence is magnified not only by its immense size but also by the density of the stars around it, all circling a gravitational abyss from which not even light can escape. If we could observe this black hole directly, which we can't, because even the Event Horizon Telescope isn't yet capable of resolving something so far away, we might see jets of energetic particles blasting from its poles, powered by matter spiraling in at incredible speeds. These jets could stretch for hundreds of thousands of light-years, lighting up the surrounding space in radio and X-ray wavelengths. The hot, X-ray bright gas that fills the center of Abell 2029 might be partially energized by this central engine, its activity influencing the entire cluster's core. The formation of such a behemoth would have been a long and violent process. Just as IC 1101 itself grew by merging with smaller galaxies, its black hole likely grew through the mergers of smaller black holes that each galaxy carried in its center. Over billions of years, these mergers, along with the steady feast of stars, gas, and dust, would have inflated the black hole to unimaginable proportions. In the process, it may have played a critical role in shutting down new star formation in IC 1101, blasting out so much energy that cold gas was heated and prevented from collapsing into new stars. From a distance, the black hole would be invisible against the glow of the surrounding galaxy. But if you were unlucky enough to venture too close, you would find yourself drawn into a region of warped spacetime where the laws of physics as we know them break down. The event horizon would be the point of no return, and once crossed, every path would lead inevitably to the singularity, the black hole's infinitely dense core. Around this abyss, a swirling accretion disk of superheated matter could shine brighter than entire galaxies, powered by the most efficient energy conversion in nature, gravity's inexorable grip on matter falling inward. In the cosmic hierarchy of giants, IC 1101's central black hole would be a king among kings, not merely massive, but among the most massive black holes the universe could possibly produce. It is a fitting heart for a galaxy that itself reigns as one of the largest known structures of stars in the cosmos. When we gaze at IC 1101 through the lenses of our most powerful telescopes, we're not seeing it as it exists right now. We're peering across a gulf of space so vast that the light from this colossal galaxy has taken roughly 1 billion years to reach us. That means every photon entering our eyes or striking a telescope sensor tonight began its journey when Earth's continents were in different positions, when the first complex life was still evolving in our oceans, and when the human species didn't exist, not even as a concept waiting in the distant genetic future. In that sense, observing IC 1101 is like opening a time capsule. The light we detect today left the galaxy during an era when the universe itself was younger, when our own Milky Way was still quietly forming stars at a much higher rate, and when Abell 2029 was still in the middle of its slow gravitational dance, drawing in new members from the surrounding cosmic web. If you could somehow see IC 1101 as it is right now, 1 billion years after the light we're currently seeing was emitted, it might already be larger, brighter, or even richer in captured galaxies than the version we know. This isn't a special effect unique to IC 1101, it's simply how the universe works. The farther away an object is, the older the light we see from it. For nearby galaxies like Andromeda, this delay is only a couple of million years, which is short by cosmic standards. But for IC 1101, the delay is staggering, reminding us that astronomy is as much a study of the past as it is of the present. Every time we push our telescopes to greater distances, we look deeper into history, catching glimpses of what the cosmos looked like long before Earth was even born. It's worth pausing to think about what that means for a moment. When those ancient photons left IC 1101, they began a journey that would carry them across unimaginable stretches of emptiness. Along the way, they would be stretched by the expansion of the universe, a process called redshift, which shifts their colors toward the longer, redder wavelengths of the spectrum. By the time they arrive here, they carry with them not just the image of IC 1101 as it once was, but also a subtle fingerprint of how space itself has changed during their billion-year trek. So when we admire an image of IC 1101, we're not just looking at a photograph of a distant galaxy. We're looking at a portrait painted in ancient light, bearing witness to a time long gone. It's a reminder that the night sky is a tapestry woven not from what is, but from what was, a living museum of cosmic history. And in that museum, IC 1101 is one of the grandest exhibits, shining from across the ages, telling us not only about itself, but about the universe as it was when its light first began its long, patient journey to our world. If we want to truly appreciate IC 1101's scale, we have to set it side by side with other large galaxies, the cosmic heavyweights that normally dominate any discussion of galactic size. Let's start with something close to home, the Andromeda Galaxy, our nearest large neighbor. Andromeda spans about 220,000 light-years across, making it roughly twice the diameter of the Milky Way and massive enough to inspire awe on its own. If Andromeda were the biggest city in a country, IC 1101 would be the size of a continent. In fact, you could line up nearly 30 Andromedas, edge to edge, before you'd match the full span of IC 1101. Moving farther afield, there's ESO 383-76, a giant elliptical galaxy often cited as one of the largest known. This galaxy measures about 1.1 million light-years in diameter, already a staggering size that makes most galaxies look modest. But even ESO 383-76 would be swallowed many times over by IC 1101. You'd need almost 6 ESO 383-76s stacked side by side to match IC 1101's more than 6 million light-year expanse. It's like comparing a massive ocean liner to a chain of islands, impressive on their own, but tiny against the scale of a continent-spanning superstructure. Even other well-known giant ellipticals like M87, famous for hosting the first black hole ever imaged, pale in comparison. M87 stretches about 980,000 light-years across, vast enough to contain our local group of galaxies within it, yet IC 1101 is still more than 6 times larger. In the same way that skyscrapers are dwarfed by mountain ranges, these colossal galaxies are still small fry next to the true supergiants of the cosmos. What's most mind-bending is that IC 1101 doesn't just edge out these other giants, it completely redefines the upper limit of what we think galaxies can be. While many massive ellipticals hover around the million light-year mark, IC 1101 shatters that ceiling and keeps going, its faint outer halo of stars stretching across distances so enormous that it's hard to even picture them without resorting to analogy. Imagine the Milky Way as a coin. In that scale, Andromeda might be a small plate, ESO 383-76 would be a large dinner plate, and IC 1101 would be a banquet table, and you'd still have to squint to see its edges. These comparisons do more than just put IC 1101's size into perspective. They highlight how rare such behemoths truly are. Most galaxies, even large spirals like our own, would be mere specks inside IC 1101's domain. It's as if nature, once in a great while, decides to push the limits of its own designs, creating something so oversized that it almost feels like an accident, the cosmic equivalent of a redwood tree towering above a forest of pines. If IC 1101 were to suddenly replace the Milky Way, not just in mass, but in sheer physical size, our entire understanding of what it means to live in a galaxy would change overnight. The Milky Way, at about 100,000 light-years across, comfortably fits the Sun and its neighboring stars within a cozy galactic disk, with plenty of space between us and our nearest galactic neighbors. But IC 1101, stretching over 6 million light-years from end to end, would swallow that concept whole and keep going. In fact, if you centered IC 1101 where the Milky Way currently sits, its edges wouldn't just extend past our local group, the small family of galaxies that includes Andromeda, the Triangulum Galaxy, and dozens of dwarf galaxies. It would stretch so far that it would engulf most of the Virgo supercluster. That's a region of space containing thousands of galaxies, bound together loosely by gravity, stretching across about 110 million light-years. IC 1101 wouldn't take all of it, of course, but it would sweep up an enormous fraction of its core regions, its vast halo overlapping with multiple other galactic systems that, in our universe, are separated by millions of light-years of emptiness. From our perspective here on Earth, this would be a radical shift in the appearance of the night sky. In the Milky Way, we see the stars of our galaxy scattered in a great band across the sky, with the nearest large galaxies appearing as faint smudges if you know where to look. But inside IC 1101, those faint smudges wouldn't be smudges at all. They would be embedded right inside the same galaxy as us, spread across the heavens like brilliant cities in a boundless golden empire. The concept of intergalactic space would become meaningless to most observers because the distances between bright star systems belonging to IC 1101 would be shorter than many of the distances between outer stars of the Milky Way and its own satellites. The Sun, if it even existed in such an environment, would be just one among hundreds of trillions of stars, and the odds are high that our local stellar neighborhood would be much more crowded. The sky could be lit with thousands of visible stars brighter than anything we see today, not because they're intrinsically more luminous, but because they would simply be so much closer on average. Nebulas and star clusters from across the galaxy could appear as luminous patches large enough to rival the Moon in size. And if IC 1101's core lay anywhere near us, its central regions could dominate the sky as a glowing mass of densely packed stars, a sight that might outshine even the Sun in certain wavelengths. In such a colossal home, the distances we currently think of as far inside the Milky Way would feel trivial. Traveling from one star system to another, in theory, would still be unimaginably challenging for a species like ours, but the sheer number of neighboring systems within any given volume of space would explode. Entire civilizations could rise and fall without ever needing to leave the gravitational embrace of IC 1101, and still have billions of unexplored worlds right in their cosmic backyard. When you realize that replacing the Milky Way with IC 1101 would effectively erase the boundaries between many currently separate galaxies, it drives home just how absurdly huge this galaxy is. It's not just bigger in a way that scales up neatly, it's bigger in a way that rewrites the very geography of the universe around it. Living inside IC 1101 wouldn't just mean living in a galaxy, it would mean living in a small universe of your own. The raw energy output of IC 1101 is staggering on a scale that defies everyday comprehension. Imagine the combined light of 100 trillion stars, each one pouring out photons in every direction, every second, without pause. Many of these stars are as bright as or brighter than our Sun, and while some are cooler, aging red giants radiating a steady amber glow, others are still massive and hot enough to blaze in the ultraviolet. Together, they produce a torrent of energy so immense that it could illuminate trillions of Earths as brightly as midday, and still have power left to spare. If you could somehow gather all of IC 1101 stars into a single point, their combined luminosity would outshine the Milky Way hundreds of times over. Even spread across its enormous 6 million light-year expanse, the galaxy radiates enough light to be a dominant presence in its corner of the cosmos. Its brilliance spills outward, mixing with the glow of surrounding galaxies in the Abell 2029 cluster, adding to a vast ocean of starlight that seeps through intergalactic space. This glow is so persistent and widespread that sensitive instruments can detect it as diffuse light even between the galaxies themselves, a testament to the scale of stellar populations that have been flung far from their home systems by past gravitational encounters. Yet here's the irony: for all that unimaginable brightness, IC 1101 remains completely invisible to the naked eye from Earth. At a distance of 1 billion light-years, even something so luminous is smeared into faintness by sheer distance. Without the aid of powerful telescopes, the light is simply too spread out, too diluted over the immense gulf of space, to register in human vision. If our eyes were replaced with detectors sensitive enough to gather and amplify those photons, IC 1101 would likely dominate a patch of sky with a soft golden glow, its vast elliptical form stretching farther than the moon's apparent diameter many times over. But to us as we are, it's a ghost in the dark, a silent powerhouse blazing unseen beyond the reach of our unaided senses. When astronomers measure its total light output, they have to account not only for the stars bound tightly to the galaxy's main body, but also for the stars in its extended halo, a region so diffuse and faint that it almost blends into the background of space itself. This halo is full of ancient stars, stripped from smaller galaxies over billions of years, their combined contribution forming a subtle but significant share of IC 1101's total luminosity. Adding up the main body and the halo gives an energy budget so enormous that it could rival some of the brightest quasars in the early universe, even though IC 1101 doesn't currently blaze with the same kind of high-energy activity. It's a humbling thought that here, in our night sky, there are points of light, single stars, that appear brighter to our eyes than IC 1101 does, simply because they are near. And yet, if we could somehow transport ourselves to just a few million light-years from IC 1101, it would be an entirely different story. Its golden heart would shine so brightly that it could cast shadows, and the surrounding sky would shimmer with countless suns from the galaxy's sprawling structure. The reality is that IC 1101 is not just a galaxy, it is a light engine on a cosmic scale, a monument to the energy locked in stars, burning for billions of years and spilling their brilliance into the darkness. For all its staggering size and luminosity, IC 1101 is not a place where new stars are born in abundance. Like many giant elliptical galaxies, it is remarkably poor in the cold gas and dust that act as the raw materials for stellar nurseries. In galaxies such as our Milky Way, vast clouds of hydrogen and interstellar dust drift through the spiral arms, condensing under gravity into dense pockets where nuclear fusion ignites and new suns are born. IC 1101, however, has largely exhausted that stage of its life. The cosmic factories are mostly shut down. The reasons for this scarcity are tied directly to the galaxy's history. Over billions of years, IC 1101 grew by consuming other galaxies, a process that tends to strip away much of the cold gas they might carry. Collisions and mergers trigger short-lived bursts of star formation, burning through the available fuel rapidly. But once the gas is used up or heated to extreme temperatures during these violent interactions, it becomes difficult for the galaxy to cool it back down to the point where it can collapse into new stars. In massive galaxies like IC 1101, the deep gravitational well and the surrounding hot intergalactic medium keep much of this gas in a heated state, preventing it from condensing. What remains is a stellar population dominated by older, cooler stars, mostly yellow and red giants, that contribute to the galaxy's overall golden hue. The absence of bright blue, short-lived stars, which are hallmarks of active star-forming regions, gives IC 1101 a calm, almost aged appearance. It's as though it has moved past the chaotic youth of starburst activity and settled into a quiet maturity, shining steadily with the light of billions of suns that formed long ago. Dust, too, is in short supply. In spiral galaxies, dust grains scatter and absorb light, often forming dramatic dark lanes and silhouetted patterns across bright star fields. But in IC 1101, the smooth, nearly featureless glow is a sign of how little dust is left. Most of it has been swept up, destroyed, or locked away in older stars. Without dust and dense molecular clouds to seed new star systems, the galaxy's stellar population will gradually age and fade over cosmic time, its brightness slowly diminishing as the most luminous stars burn out. This doesn't mean IC 1101 is entirely dead in terms of star formation. Even giant ellipticals can harbor small pockets of activity, often in their outskirts or from occasional infusions of material from smaller infalling galaxies. But compared to a spiral galaxy teeming with blue newborn stars and gas-rich nebulae, IC 1101 is in a much quieter, more settled phase of life. It is the difference between a bustling city full of construction cranes and a vast, ancient metropolis whose towers have long been finished, glowing warmly in the evening light. IC 1101 doesn't just sit in the dark void of space, it's immersed in an environment that literally glows with invisible light. The galaxy resides in the heart of the Abell 2029 cluster, and this colossal congregation of galaxies is wrapped in an enormous halo of superheated gas. This gas isn't warm in the way we think of air on a summer day. It is heated to tens of millions of degrees Celsius, hot enough that atoms are stripped of their electrons and the whole medium becomes a plasma. At such extreme temperatures, the gas doesn't shine in visible light, it radiates in X-rays, pouring out high-energy photons that our eyes cannot see but which space-based observatories can detect with ease. When telescopes like NASA's Chandra X-ray Observatory turn their gaze toward Abell 2029, the result is a ghostly, glowing image of the cluster's core, where IC 1101 resides. This glow comes from the thermal Bremsstrahlung radiation, a process where charged particles are violently deflected by atomic nuclei, releasing energy in the X-ray part of the spectrum. The hot plasma fills the space between galaxies in the cluster, stretching across millions of light-years, and IC 1101 is completely bathed in it. The presence of this searingly hot gas has profound effects on the galaxy itself. First, it acts as a kind of barrier to future star formation. Even if IC 1101 were to capture cold gas from an unlucky smaller galaxy that strayed too close, the cluster's X-ray emitting environment would heat it quickly, preventing it from cooling enough to collapse into new stars. Second, this environment is a product of the cluster's immense gravitational pull. Only a system as massive as Abell 2029, with a combined gravity of thousands of galaxies and vast amounts of dark matter, can hold on to so much hot gas without it dispersing into intergalactic space. In a way, the X-ray glow is like the faint heat haze rising from a desert, except here the desert is an ocean of plasma extending farther than entire galactic diameters. And IC 1101, sitting at the gravitational center, is at the heart of this cosmic furnace. The galaxy's own gravitational influence also helps keep part of this gas bound near its core, feeding any active processes within, possibly even its central black hole, though not in the spectacular, quasar-like fashion of younger galaxies. For astronomers, this glow is not just a pretty picture, it's a diagnostic tool. By studying the X-ray spectrum, scientists can measure the temperature, density, and chemical composition of the gas, revealing the history of star formation and galaxy mergers within the cluster. Elements like iron, oxygen, and silicon, forged in ancient stars and scattered by supernovae, enrich the plasma and leave distinctive fingerprints in the X-ray data. This tells us that the glow surrounding IC 1101 is more than just hot hydrogen. It is a soup of cosmic history, a byproduct of billions of years of stellar evolution. In the end, the X-ray halo of Abell 2029 is both a cage and a crown for IC 1101, a cage, because it keeps the galaxy locked in a state of low star formation, and a crown, because it marks the galaxy's reign over one of the most massive and luminous clusters we know. IC 1101 is already one of the largest galaxies ever observed, yet its story is far from over. In the vast, slow dance of cosmic evolution, time is its greatest ally. Over the next several billion years, this colossal elliptical will almost certainly grow even larger as it continues to feed on the galaxies of Abell 2029. The cluster is a gravitational trap on a mind-bending scale, and IC 1101, sitting at its very center, is the ultimate sink for anything that drifts too close. Gravity in galaxy clusters works like an invisible web. Every galaxy, every cloud of gas, every starless lump of dark matter is connected by this web, drawn subtly but persistently toward the most massive point, and in Abell 2029, that point is IC 1101. Many of the smaller galaxies in the cluster are already on trajectories that will lead them into the giant's embrace. These mergers will happen slowly from our point of view, 1 billion years here, 2 billion years there, but in cosmic terms, they're inevitable. Each collision will add more stars, more dark matter, and occasionally fresh bursts of energy into IC 1101's already enormous bulk. Interestingly, these future mergers will not make IC 1101 a hotbed of new star birth, because most of the incoming galaxies are likely to be gas-poor themselves, especially in the harsh, X-ray glowing environment of Abell 2029. Instead, the mergers will mostly add older stars to its collection, further increasing its already staggering population while reinforcing its golden, mature glow. Its profile will likely remain smooth and elliptical, the chaotic spiral arms and bright blue knots of star formation long gone from its youth. The growth of IC 1101 is also bound up with the fate of the cluster itself. Abell 2029, like all galaxy clusters, is held together by its massive dark matter halo. As the universe continues to expand and dark energy accelerates that expansion, the cluster will eventually become more isolated from the rest of the cosmos. Galaxies within it will still interact and merge, but the inflow of new material from outside the cluster will slow to a trickle. Over unimaginable spans of time, tens or even hundreds of billions of years, IC 1101 may end up as the last great structure standing in a dimmed, aging cluster, surrounded by little more than the scattered remnants of other galaxies it has long since consumed. Some astronomers even speculate that if the process continues far enough, IC 1101 could evolve into something like a fossil galaxy, a single, enormous elliptical containing nearly all of the luminous matter from its original cluster, floating alone in a universe that has grown cold and dark. In that distant future, the galaxy could span distances that would make its current 6 million light-years seem modest by comparison. For now, though, IC 1101's future is a slow but relentless process of accumulation. Every gravitational encounter, every close pass, every stray galaxy wandering into the heart of Abell 2029 will add another layer to this cosmic titan. It is not done growing, and given enough time, it may yet claim the undisputed title of the largest galaxy the universe has ever known. Galaxies like IC 1101 are not just rare, they are the crown jewels of the cosmos, the extraordinary products of conditions that exist in only a tiny fraction of the universe. Most galaxies we see, even with powerful telescopes, are far smaller and less massive. Spiral galaxies like our Milky Way or Andromeda are fairly common, and even large ellipticals are not unusual in dense regions of space. But a supergiant elliptical spanning over 6 million light-years and housing hundreds of trillions of stars is something you only find in the most extreme environments, the cores of the most massive galaxy clusters. The reason for this rarity is straightforward but profound. To build something on the scale of IC 1101, you need not only a colossal supply of matter, stars, gas, dark matter, but also billions of years for gravity to gather it together. These conditions are met only in regions of space where the gravitational pull of an enormous dark matter halo has drawn in thousands of galaxies over time. Abell 2029, the home of IC 1101, is one such place. Without the cluster's gravitational well to pull galaxies toward the center, IC 1101 would never have had the opportunity to grow so massive. In smaller clusters or groups, galaxy mergers still occur, but they rarely produce anything of this magnitude. There simply isn't enough raw material, and the mergers don't happen frequently enough. Even among the central galaxies of large clusters, IC 1101 stands out for its sheer size and mass. It is, in many ways, an outlier among outliers. When astronomers search for similar giants, they often find nothing quite like it. The universe is vast, but the combination of factors that made IC 1101 what it is today, a prime location in a megacluster, a history of countless mergers, and a gravitational grip strong enough to keep pulling in new matter, is extremely unusual. There's also the role of cosmic time to consider. The universe is 13.8 billion years old, but structures like IC 1101 take most of that time to form. If we looked back to a time when the universe was only a few billion years old, we would find that even the largest galaxies then were smaller than today's giants. IC 1101 is a product of the universe's long maturity, a peak in galactic evolution that's only possible now that so many galaxies have had time to merge. In the far future, such titans may become more common, but by then, the accelerating expansion of the universe may have isolated each galaxy cluster so much that these giants will be forever hidden from one another. This rarity also makes IC 1101 scientifically precious. Because so few galaxies reach this size, studying it gives astronomers a unique window into the processes that drive extreme galactic growth. It's like finding a single, massive redwood tree towering over an otherwise ordinary forest, a sign that the local conditions were somehow perfect for producing something extraordinary. And so, IC 1101 isn't just large, it's exceptional. Out of the countless billions of galaxies scattered across the universe, only a handful are even in the same league. Its existence is a reminder that the cosmos, for all its immensity, still produces rare wonders, and that sometimes, even among galaxies, there are those that stand far above the rest. When we talk about IC 1101, we're not speaking about a galaxy we can casually peer at through a backyard telescope. It lies roughly a billion light-years away, so far that even the most powerful amateur instruments would show nothing but an empty patch of sky. Detecting and studying something at that distance requires the combined power of the largest ground-based observatories and space-based telescopes, along with a deep understanding of how light behaves over cosmic scales. The first and most important tool in this process is redshift. Because the universe is expanding, light from distant galaxies is stretched as it travels toward us, shifting toward longer, redder wavelengths. The degree of this shift tells astronomers how fast the galaxy is receding from us, which in turn allows them to calculate its distance. In the case of IC 1101, its redshift reveals that its light has been traveling for about a billion years before reaching our eyes. That's not just a measure of distance, it's also a look back in time, to when the galaxy was a billion years younger than it is today. Once we know where to look and how far away it is, we can start to measure its physical properties. This is where telescopes, both optical and multi-wavelength, come into play. Ground-based giants like the Keck Observatory in Hawaii or the Very Large Telescope in Chile can collect faint visible light from IC 1101, while space telescopes like Hubble can observe it without the interference of Earth's atmosphere. But even optical light isn't the whole story. X-ray observatories like Chandra, infrared instruments like Spitzer, in its time, and radio telescopes like ALMA all contribute pieces of the puzzle. Measuring IC 1101's actual size is a challenge in itself. Astronomers can't physically see the edges of the galaxy the way you might trace the rim of a coin. Instead, they use brightness profiles, precise measurements of how the galaxy's light fades as you move outward from its center. In a supergiant elliptical like IC 1101, the light doesn't abruptly end. It gradually diminishes, blending into the faint glow of stars that extend far beyond the bright core. Determining where the galaxy ends becomes a matter of defining a threshold, often based on how the brightness falls compared to the surrounding background. This is complicated by the fact that IC 1101 lies in the middle of a dense galaxy cluster. The faint outer halo of its stars overlaps with the intracluster light, a diffuse glow made of stars stripped from other galaxies during collisions and mergers. Separating IC 1101's light from this background haze requires careful modeling and sometimes computer simulations to reconstruct what belongs to the galaxy itself. There's also the challenge of the sheer faintness of those outer regions. Even for a galaxy as massive as IC 1101, stars at its edge are spread so thin that their combined light is almost imperceptible. Long exposure imaging, stacking multiple observations, and using sensitive detectors are essential to tease out those final traces of starlight from the noise. In short, studying IC 1101 is as much about detective work as it is about direct observation. We measure its distance with redshift, trace its light with enormous telescopes, and model its shape and structure with sophisticated brightness profiles. Every bit of data we gather is hard-won, pulled from the faintest whispers of light that have traveled for 1 billion years just to tell us the story of one of the largest galaxies in the universe. If we could somehow transport ourselves to a planet orbiting a star deep within IC 1101, the night sky would be unlike anything we've ever experienced in the Milky Way. Our galaxy, even in its densest regions, leaves plenty of dark space between the stars. On Earth, we can see a few thousand stars with the naked eye, even from a perfectly dark location. But in IC 1101's crowded core, that number would explode into the millions, perhaps tens of millions, visible without any aid. The sky wouldn't just be dotted with points of light, it would be drenched in them, so thick and bright that darkness itself would seem like a rare visitor. Most of these stars would glow with a warm, golden hue, a reflection of the galaxy's ancient population. You wouldn't see the brilliant blue-white of massive young stars because IC 1101 has long since passed its era of active star formation. Instead, your world would be bathed in the soft amber light of countless elderly suns, each burning steadily but more gently than the hot blue stars of a younger galaxy. The collective glow would give the entire sky a subtle golden wash, as if the heavens themselves were dusted in starlight. In the core, the density of stars could be hundreds or even thousands of times higher than what we know here. Nearby stars might be close enough to cast shadows, not as strongly as a sun, but enough that you could read by their light if your eyes adapted. In fact, night in the conventional sense might barely exist at all in some regions. The perpetual glow of neighboring stars would keep the sky in a constant twilight, even when your own sun dipped below the horizon. Looking outward, you might spot the faint shimmer of IC 1101's sprawling halo, not as a sharp structure, but as an immense, diffuse background haze that never truly ends. And here's the most astonishing part: even with such a brilliant foreground of stars, you would still see other galaxies. Remember, IC 1101 lies in the heart of Abell 2029, a city of thousands of galaxies. Some would hang in your sky like bright smudges, others like glittering islands, each one a separate realm of hundreds of billions of stars. In the densest parts of the cluster, entire galaxy groups could appear clustered together, giving the sky a layered, three-dimensional feel that would be almost overwhelming to comprehend. And if you look toward the very center, assuming you were orbiting a star a bit farther out from the galactic core, you might see an intense, dazzling region marking the heart of IC 1101, where stars, gas, and possibly the radiation from a supermassive black hole converge into a brilliant hub. That core could outshine everything else, a golden beacon surrounded by the quieter glow of the outer galaxy. It would be a place where the concept of isolation between stars all but disappears. The Milky Way feels spacious and lonely at times, vast regions of emptiness broken only by scattered points of light. But in IC 1101, space would feel crowded, alive, and saturated with the presence of other suns. Every direction you looked would be a reminder that you were living in one of the most populated stellar cities the universe has ever built. Studying IC 1101 is like opening a history book written on the grandest possible scale. Every faint glow in its halo, every curve in its brightness profile, every gravitational tug it exerts on its neighbors tells us something about how the universe builds its largest structures. This is not just an overgrown galaxy. It is a living record of cosmic evolution, an archive of billions of years of collisions, mergers, and gravitational interactions. By examining IC 1101, astronomers gain insight into the processes that sculpt galaxies from infancy to old age, particularly at the extremes of size and mass. One of the first lessons IC 1101 teaches is about the upper limits of galactic growth. We know galaxies don't just keep expanding forever without limit. There are natural constraints imposed by their environments, by the availability of matter, and by the physics of gravitational binding. IC 1101 shows us what happens when a galaxy exists in a rich, dense cluster environment for billions of years, with an unending buffet of smaller galaxies to consume. It's a case study in how large-scale structure funnels mass inward, building up a central dominant galaxy, known as a CD galaxy, to unprecedented proportions. It also gives us valuable data on stellar populations in massive ellipticals. Because IC 1101 is composed mostly of older, redder stars, astronomers can test theories about how star formation shuts down in giant galaxies. This process, often referred to as quenching, is thought to be driven by factors such as active galactic nuclei heating surrounding gas, or the hot intracluster medium preventing new cold gas from falling in. IC 1101's lack of young stars and its enormous mass make it a perfect laboratory for studying how galaxies transition from blue, star-forming spirals to red, dormant ellipticals. The galaxy's position in the heart of Abell 2029 also sheds light on how galaxy clusters themselves evolve. Central galaxies like IC 1101 aren't just passive residents, they influence the entire cluster. Their gravitational dominance shapes the orbits of other galaxies, affects the distribution of dark matter, and may even help regulate the temperature and density of the cluster's hot gas through feedback processes from their central black holes. Observing IC 1101 lets scientists see these dynamics in action, helping to refine our understanding of how clusters remain stable over billions of years. Even its faint outer regions carry deep significance. The diffuse halo of IC 1101 blends into the intracluster light, which is made up of stars stripped from galaxies during violent interactions. By mapping this faint light, astronomers can reconstruct the cluster's violent history, which galaxies collided, how much mass was lost, and how the cluster's structure has shifted over time. In this way, IC 1101 becomes a forensic tool, revealing the slow but relentless processes that turn a loose gathering of galaxies into a tightly bound cosmic metropolis. Beyond the specifics of its own structure, IC 1101 serves as a benchmark for simulations of galaxy formation and evolution. Computer models that attempt to recreate the universe from its earliest moments must be able to produce objects like IC 1101 under the right conditions. If a simulation can't form such a galaxy, it suggests something is missing from our understanding, perhaps about dark matter distribution, merger rates, or the physics of star formation in dense environments. Conversely, matching the observed properties of IC 1101 in a simulation validates the models and boosts our confidence in the broader theories of cosmology. In essence, IC 1101 is both a destination and a mirror. It stands as one of the grandest end products of cosmic growth, but in studying it, we also reflect back on the journey, the billions of years of expansion, the countless galactic collisions, and the steady sculpting hand of gravity that shaped not only IC 1101, but every galaxy in the universe, including our own. Imagine holding a coin in your hand, let's say a quarter, about an inch across. That's our Milky Way. Now, place it on a table, and next to it set down a full-sized dinner plate, maybe a foot across. That plate is IC 1101. Already, the difference feels absurd. The Milky Way, with its 100,000 light-year diameter, is no small thing. It contains hundreds of billions of stars, countless worlds, and vast spiral arms stretching across space. Yet compared to IC 1101, it's like comparing a modest family home to an entire continent. And here's the kicker, even that dinner plate analogy undersells it. If we wanted to be completely accurate in terms of scale, the coin would have to shrink to something smaller than a pea, while the dinner plate might have to expand into the size of a large serving tray. IC 1101 isn't just a bit bigger, it's about 60 times larger in diameter than our Milky Way. And because volume scales with the cube of the radius, that means its total volume of stars, gas, and dark matter is millions of times greater. Think about what that means spatially. If you replaced the Milky Way with IC 1101 and kept our Sun in roughly the same location, the farthest reaches of its halo would extend far, far beyond the Andromeda Galaxy, past dozens of other galaxies in our local group, and out into territory we now think of as part of the Virgo supercluster. From our perspective here on Earth, we wouldn't just be living in a galaxy, we'd be in a galactic nation sprawling so far across the sky that it would take up most of it. Even in terms of light travel time, the difference is staggering. Light can cross the Milky Way in about 100,000 years, a long trip by any standard. But crossing IC 1101 from one side to the other would take over 6 million years at the speed of light. Imagine sending a signal from one side of your galaxy city to the other and having to wait 60 centuries just for the light to reach its destination. That's how immense this structure truly is. If we apply the same coin-to-plate visualization to other big galaxies, we find that IC 1101 still dominates. The Andromeda Galaxy might be represented by a slightly larger coin than the Milky Way's, but it would still sit looking humble beside the vast expanse of the plate. Even giant galaxies like ESO 383-76, which are themselves considered monsters, would fall far short. This helps us wrap our minds around the scale difference in a way that raw numbers sometimes can't convey. Numbers like 6 million light-years or 60 times larger are staggering, but they're abstract. Seeing it as something you can hold in your hands, a tiny coin beside a massive plate, transforms the unimaginable into something tangible. And yet, the analogy only scratches the surface. Because IC 1101's halo extends so faintly and so far, the plate in our mental image might need to fade gradually into the surrounding space, blending with the intracluster light of Abell 2029. It's not just a rigid boundary, it's a sprawling, diffuse city whose edges blur into the very fabric of its environment. If you could somehow fly to its outer rim and look back, you might not even be able to tell where IC 1101 ends and the cluster begins. That's how enormous, and how intertwined with its surroundings, this galaxy truly is. The heart of Abell 2029 is anything but still. Despite the calm, golden glow of IC 1101 stars, the space around it is a seething arena of gravitational forces, where thousands of galaxies move like cosmic dancers in a tightly choreographed yet chaotic ballet. These galaxies are not drifting aimlessly, they are bound together by the enormous gravity of the cluster's combined mass, the stars, gas, and especially dark matter that form its hidden skeleton. And at the very center of this gravitational web sits IC 1101, the ultimate collector in a game that has been going on for billions of years. In this environment, gravitational interactions are inevitable. Smaller galaxies wander too close to IC 1101 and feel the irresistible pull of its gravity, which is amplified by the deep potential well of the entire cluster. Some of these encounters are slow, drawn-out dances where the smaller galaxy is gradually stretched, distorted, and stripped of stars and gas over millions of years. Others are more direct collisions, where two galaxies merge in a violent flash of stellar fireworks, though in IC 1101's case, the fireworks are mostly from gravitational heating and brief spurts of star formation rather than long-lived bursts. The intracluster medium, that vast cloud of superheated gas filling Abell 2029, plays its part in this process too. Galaxies passing through this hot plasma experience what astronomers call ram pressure stripping, where the pressure of the gas effectively blows away a galaxy's own cold gas reservoir. This strips them of their ability to form new stars and turns them into gas-poor husks, which are then easier for IC 1101 to absorb without triggering massive bursts of star formation. Over time, the stripped stars from these satellites join IC 1101's halo, building it layer by layer like a massive snowball rolling downhill. Dark matter also plays a crucial role. The entire cluster is wrapped in a massive dark matter halo, and IC 1101's own dark matter envelope is nested inside it. This means the galaxy's reach is even greater than its visible size. The gravitational influence extends far beyond where the eye, or even the most sensitive telescope, can detect light. This invisible hand helps draw in matter from across the cluster, subtly altering the orbits of neighboring galaxies and gradually feeding IC 1101's growth. The process is relentless. Abell 2029 is a highly relaxed cluster, meaning it's been gravitationally bound and stable for billions of years, so the motions of its galaxies are relatively smooth compared to younger, more chaotic clusters. This stability actually benefits IC 1101's growth, because it allows more gradual mergers to occur without the whole cluster being disrupted. Over cosmic timescales, these constant interactions act like a slow but steady conveyor belt, delivering new mass to the central galaxy. In the end, IC 1101 isn't just a passive bystander at the center of Abell 2029, it is the anchor around which the entire cluster moves. Every orbit, every gravitational tug, every lost star in this vast metropolis of galaxies ultimately helps feed its growth. And given enough billions of years, the giants of the cluster will continue to spiral inward, adding even more to its staggering size until IC 1101 becomes an even greater titan than it is today. IC 1101's story begins in the deep dawn of the universe, not long after the Big Bang itself. Around 13.8 billion years ago, the cosmos was a hot, dense sea of energy and particles, rapidly expanding and cooling. In those first moments, matter was spread out almost evenly, but not perfectly. Tiny quantum fluctuations from the earliest instance of time left behind faint irregularities, slight overdensities in the otherwise uniform distribution of matter. These were the seeds of everything to come. As the universe expanded and cooled, gravity began working on those tiny overdense regions, pulling more matter toward them. Over tens of millions of years, the first protogalaxies began to form in these gravitational wells. In the region that would one day become Abell 2029, one such overdensity began to accumulate matter at a faster rate than its neighbors. This was the ancestral core from which IC 1101 would emerge. Roughly 1 to 2 billion years after the Big Bang, the first generation of galaxies in this region had already taken shape. These early galaxies were small, chaotic, and gas-rich, forming stars at furious rates. But their orbits, influenced by the growing cluster's gravity, brought them into repeated encounters with one another. Some collided head-on, merging into larger systems. Others simply passed close enough to be stripped of stars and gas. Over time, the largest galaxies grew at the expense of the smaller ones, a process astronomers call hierarchical assembly. By around 3 to 4 billion years after the Big Bang, the central galaxy of this growing cluster, the early IC 1101, had already become a behemoth by the standards of the time. It was likely a massive elliptical even then, the result of repeated mergers between smaller spirals and irregulars whose original shapes had been erased by the violence of their collisions. The galaxy continued to grow, not in a sudden burst, but through a steady diet of mergers and accretions. Over the next several billion years, the surrounding cluster matured into the colossal Abell 2029 we see today. As it did, IC 1101's growth shifted from rapid, gas-rich mergers, which triggered intense star formation, to slower, gas-poor mergers, in which older galaxies without much cold gas simply merged their stars into the central giant without creating many new ones. This is one reason IC 1101 now appears so golden and quiescent. Most of its star-forming days are long behind it. For about the past 10 billion years, IC 1101 has been in this steady growth phase, gradually increasing its size and mass through the cannibalization of other galaxies. This is a timescale almost impossible to grasp. Human civilization has existed for only a few thousand years, while this galaxy has been building itself up for a period thousands of times longer than all of human history combined. Even now, the process hasn't stopped. IC 1101 continues to grow, albeit at a slower pace than in its youth. Every galaxy that drifts too close and loses its orbit to the gravitational pull of the cluster's core will eventually become part of its sprawling halo. Over the next several billion years, it will likely consume many more of its neighbors, adding their stars to its already immense population. In this way, IC 1101 is both ancient and still unfinished, a living relic from the universe's earliest times that continues to evolve. For all its breathtaking size, IC 1101 might not be the undisputed heavyweight champion of the universe. It holds the title of one of the largest known galaxies, but that small phrase "known" carries a lot of weight in astronomy. Our ability to declare any galaxy the biggest depends entirely on what we can see, and the truth is, our view of the universe is far from complete. The observable universe stretches for about 93 billion light-years across, and yet every deep-field image, every survey, every galaxy catalogue we've ever compiled still covers only a tiny fraction of that vast expanse. There are entire swaths of space we simply can't see, not because they're too far away for light to have reached us, but because other cosmic structures block our view. One example is the zone of avoidance, where the thick dust and stars of our own Milky Way obscure the light from galaxies lying beyond. It's entirely possible that behind that curtain of cosmic clutter, galaxies as large as or larger than IC 1101 are hiding in plain sight. Then there's the issue of distance. The farther away a galaxy is, the fainter it appears, even if it's enormous. At extreme distances, light not only grows dim but is stretched into longer wavelengths by the expansion of the universe, a phenomenon called redshift. This makes detection even more challenging, especially for objects that don't have active quasars or bursts of star formation to make them stand out. Some galaxies could be so far away that their light is stretched entirely out of the visible range, slipping into infrared wavelengths that are harder to capture without the most sensitive instruments. Even within the universe we can see clearly, there are contenders that rival IC 1101. Giant ellipticals like ESO 383-76 or Hercules A have similarly massive scales, and while IC 1101 remains a top contender in terms of diameter, measurements aren't always straightforward. Galaxies don't have a hard edge, they fade gradually into space, with stars spread out over vast halos. Where astronomers decide to draw the line for a galaxy's size can change its ranking. It's like measuring the edge of a cloud. Depending on your definition, the size can vary significantly. Another reason we can't declare IC 1101 the absolute largest is that galaxy evolution is ongoing. Somewhere, Perhaps in the core of an even richer cluster than Abell 2029, a central galaxy could already be surpassing IC 1101 in both mass and diameter, but its light might take several billion more years to reach us. By the time we detect it, the record books might need updating. And, intriguingly, there's the possibility that galaxies in the very early universe, while not visible in their full glory yet, are in the process of becoming even bigger than IC 1101 will ever be. Some simulations suggest that in ultramassive galaxy clusters forming in dense regions of the cosmos, central galaxies could eventually grow to truly staggering proportions, potentially exceeding 10 million light-years in size. We might simply be catching IC 1101 during a particular moment in cosmic history, a giant now, but one day eclipsed by even greater behemoths. In the end, calling IC 1101 the largest known is both accurate and humble. It's a reminder that our cosmic knowledge is provisional, always subject to change as new discoveries push the limits of what we understand. Somewhere out there, hidden in the depths of space or in the glare of another galaxy cluster, an even greater titan could be waiting for its turn in the spotlight. Studying IC 1101 is a little like trying to examine the details of a lighthouse 100 miles away through a foggy, shifting atmosphere. The sheer distance alone, about 1 billion light-years, immediately makes the task daunting. Light from IC 1101 began its journey toward us when multicellular life on Earth was just starting to gain complexity, long before the first dinosaurs, long before the continents were in their current positions. Over that billion-year trek, the photons that carry the galaxy's image have been stretched and dimmed by the expansion of space itself. By the time they arrive, they are far fainter than when they began, and in some cases, shifted out of the visible spectrum entirely. Astronomers rely on extremely sensitive detectors and long exposure times to collect enough of this light to form an image. Space telescopes like Hubble and ground-based giants equipped with adaptive optics can tease out detail, but even then, we're often working with signals that are barely above the background noise of the universe. To make matters trickier, IC 1101 isn't a brilliant beacon like an active quasar or a starburst galaxy. It's a calm, old elliptical, radiating a steady, even glow that lacks the dramatic high energy flares that would make it stand out more easily from across such vast distances. Intervening cosmic dust and gas also conspire against a clear view. While space is mostly empty, it's not perfectly empty, and the light from IC 1101 passes through numerous regions of intergalactic medium on its way to us. This material can scatter and absorb light, subtly altering its color and reducing its brightness. On top of that, the Milky Way itself sits in the line of sight, and our galaxy's own dust lanes and star fields act like an intricate veil over the distant background. Even the tiniest specks of cosmic dust, on scales measured in microns, can be enough to blur and redden the light we receive. Redshift adds another layer of difficulty. Because the universe has been expanding during the entire billion years that IC 1101's light has been traveling, its spectral lines, the chemical fingerprints in its light, have been stretched toward longer wavelengths. This means that features astronomers use to measure its composition, motion, and age are shifted from their original positions, requiring precise calibration and often infrared instruments to capture them at all. Without adjusting for this, our picture of the galaxy would be incomplete or misleading. Then there's the challenge of scale. IC 1101 is so massive that defining where it ends isn't straightforward. Its stars fade gradually into the faint background light of the cluster, and distinguishing its outer halo from the surrounding population of stars in Abell 2029 requires careful modeling of light profiles. It's not like a planet with a crisp outline, it's more like a distant mountain fading into the mist, and deciding where the mountain ends and the sky begins can be subjective. All of these factors mean that every measurement we take of IC 1101, its size, mass, star count, even its brightness, comes with uncertainties. And yet, despite these hurdles, we've still managed to piece together a remarkably detailed portrait of this galaxy. That's a testament to the ingenuity of modern astronomy, combining data from optical telescopes, radio arrays, X-ray observatories, and advanced computer models to reveal the nature of something impossibly far away. The very fact that we can say anything at all about IC 1101, given these challenges, is one of the quiet marvels of science. When you think about IC 1101, it's almost impossible not to feel that deep, humbling tug in your chest, the one that comes when your brain tries, and inevitably fails, to truly grasp just how immense the universe is. We live our lives measuring distance in steps, in miles, maybe in thousands of miles when we talk about a flight or a journey around the world. The Moon, a mere 240,000 miles away, already feels unimaginably far for most of us. The Sun sits 93 million miles from Earth, and yet, all of that is nothing more than a microscopic drop compared to the scale of IC 1101. Our Milky Way, a magnificent spiral galaxy in its own right, spans about 100,000 light-years. That's already more than enough to stagger the mind. 100,000 years for light, the fastest thing in the universe, to cross it from one side to the other. Now multiply that width by 60. That's IC 1101. It's not just larger, it's in an entirely different category of existence. If our galaxy is a modest island, IC 1101 is a sprawling continent that would swallow entire archipelagos of galaxies without noticing. And the numbers don't care about our human sense of proportion. 100 trillion stars. 100 trillion suns. Imagine each of them with its own system of planets, some barren, some icy, some perhaps with oceans and mountains and skies under alien suns. That's not science fiction, that's just arithmetic extrapolation. IC 1101's potential for worlds and histories and stories dwarfs the entire human saga into something so infinitesimal it might as well be a footnote in the cosmic library. Standing on Earth, on this tiny rock that can be crossed on foot in months or flown around in hours, we are not just small, we are subatomic compared to a structure like IC 1101. And yet, somehow, from our miniature vantage point, we've managed to see it. Our telescopes have gathered its ancient light, our minds have measured its span, and our imaginations have dared to picture it. That act alone is profound. A creature whose lifespan is shorter than the blink of a cosmic eye, living on a planet the size of a speck in the galactic map, has reached across 1 billion years of time to identify a colossus it will never touch. IC 1101 stretches the imagination in another way, too. It forces us to consider time not in centuries or millennia, but in epochs. When its light began traveling toward us, dinosaurs had already been gone for hundreds of millions of years, and mammals were still small, furtive creatures. Civilizations, languages, art, and culture, all of those were still 1 billion years in the future. It's a reminder that our place in the cosmic story is fleeting, our moment here brief. And yet, here we are, peering into the deep past and contemplating a galaxy so large it redefines what large even means. There's a strange kind of comfort in that realization. If IC 1101 exists, if the universe contains structures of such magnitude, then our personal worries and dramas are put into perspective. Not in a way that diminishes their meaning for us, but in a way that shows they're part of something so much bigger, so much grander, that it's almost beautiful to feel small. To be aware of your own insignificance in the vast cosmic ocean, and still be capable of awe, might be one of the most human things of all. Somewhere in the far reaches of the cosmos, beyond 1 billion light-years of expanding space, a silent giant drifts in the heart of its cluster. It does not roar like a quasar or burst into being like a newborn star. It simply exists, vast beyond comprehension, holding together 100 trillion suns in a gravitational embrace so immense it bends the paths of entire galaxies. IC 1101 doesn't need to move quickly or flash brightly to command attention. Its sheer scale is its statement. It is the slow, steady monument to time itself, grown over billions of years through countless mergers and cosmic dances, until it became a realm so enormous that even the Milky Way is a mere speck beside it. When we think about IC 1101, we are forced to stretch our minds into uncomfortable territory. We are asked to imagine distances so great they lose all intuitive meaning, to picture the lives and deaths of stars on timescales longer than Earth has existed, and to acknowledge that, in the grand ledger of the universe, our home galaxy is a modest, middleweight structure, remarkable to us, but dwarfed in the presence of a true titan. IC 1101 doesn't just redefine our sense of big, it redefines our sense of possibility. It is a reminder that the universe is not limited to what we can see with the naked eye, nor even to what we can easily imagine. There are scales and structures beyond our daily perception that exist regardless of whether we can visit them, touch them, or even fully understand them. And yet, they are as real as the ground beneath our feet. The light from IC 1101 has traveled for 1 billion years to reach us, bearing witness to an era when our planet was young, when our continents were unrecognizable, when life as we know it had not yet emerged. To look at it is to look not only across space but across time, to peer into a deep, ancient past that still exists, in a sense, out there. If you could stand on a world orbiting one of IC 1101's ancient suns and gaze up at its sky, you might see hundreds of thousands of stars shining with a steady golden light, far brighter and more numerous than what we see from Earth. Beyond those stars, you'd see the faint hazy glow of entire galaxies within Abell 2029, scattered like embers in the dark. You'd be living inside a cosmic capital, a place where the sheer density of light and mass would make you feel as if you were truly at the center of something enormous. And yet, here we are, unimaginably far away, able to know of its existence. That, perhaps, is the most powerful thought of all, that our fragile species, bound to one small world, has found a way to measure and admire something so staggeringly far beyond us. It humbles, it inspires, and it ignites the imagination. In a universe of unimaginable giants, IC 1101 is one of the true titans, a reminder of the cosmos' vastness, of the boundless creativity of nature, and of the fact that no matter how much we think we've seen, there are wonders out there that will always exceed our ability to fully comprehend. And maybe that's the greatest gift the universe gives us, the eternal promise that there will always be something bigger, older, and more mysterious waiting to be discovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.